Okay, 7.4, we're in this last section of this unit, and we are going to apply properties of similar triangles. So again, we're just talking about similar triangles, and just a refresher, we have our angle-angle similarity, we have side-side-side similarity, and we have side-angle-side similarity. Those are the three and only three ways that we can prove triangles are similar. And remember, similar means same shape, not necessarily same size. Okay, so there's a lot of theorems that we're talking about today, and the first one is called the triangle proportionality theorem. Triangle proportionality theorem, and let's break that up. Triangle, we know what triangles are. Proportionality, that kind of sounds like the word proportional, which kind of means similar, right? And they're pushing those two things together to say theorem. So basically, if you have this picture, so if you have a triangle. What else looks important here? We have a triangle, we have a line cutting the triangle, and we have these arrows. Remember, these arrows mean parallel. So basically, when you have parallel lines in a triangle, what's going to happen is it's going to cut up the sides of that triangle so that they're proportional, they're similar. So for example, if this one was 1 and 3, and this one was 2, and I wanted to know what this one was, well, we can set it up as a proportion. 1 over 3 is going to equal 2 over x. You can cross multiply, and you would get that that side is 6. And that makes sense. So again, when you have proportional, if I was going to write this in my own words, which you should be doing, when I have a triangle, and there's a triangle, and there's parallel lines in the triangle, then the sides being cut are proportional. So that's pretty cool. So, and the reason why that happens is if you based off of what we learned last unit about last section about angle, side, and side, angle, side. If you look at this little triangle and you can compare it with a big triangle, triangle ABC, if you notice we have parallel lines, and remember parallel lines, usually I want you to think about alternate interior angles. In this case, I want you to think about corresponding angles. So we have these angles are congruent, they're corresponding, they're congruent, and they also share angle A. So these two triangles are similar, and thus their sides are proportional by angle. So this works because of angle similarity. Because you have that little one that shares angle A. So that's congruent by the reflexive puck. And then we have these are congruent by corresponding angles, or these sides will also be congruent. These angles would also be congruent as well. Excuse me. So the whole reason why that works is because of angle similarity, and how we can actually use that is, let's say we want to find US. Well, okay, again, we have a triangle. We have a triangle, we have parallel lines, so we know that these sides are going to be proportional. So there's lots of ways you can write this. I like to look at one side of the triangle at a time. So for example, 14 over x, and 14 looks like 10, so 10 over 4. And then you cross multiply and solve. So 10x equals whatever 4 times 14 is, and then you divide both sides by 10. So that's something you can put into your calculator. Go ahead and try to do number 2. My smart slate is running out of batteries. Oh my goodness. Okay. So reflection, also think about the reflection. And then the second theorem is called the converse of the triangle proportionality theorem. Remember, converse just means we're going to flip, right? We're going to flip it around. So basically what this says is, let's say I give you again that same picture with a triangle, and it looks like two lines are parallel, but they don't give us those arrows. If we find out that those sides are proportional, that's what this means. The sides are proportional. Then we can conclude that the sides are going to be parallel. So if sides are proportional, then the lines are parallel. Okay, so for example 2, it says verify, prove, show that these segments are parallel. Show that these segments are parallel. Well, to prove it, all you have to do is set up a proportion and prove that it's equal. So for example, I'm going to do one side of the triangle, 10 over 15 equals 8 over 12. And you can solve this two ways. You can either put in calculator and give me the decimal. But since on the state test you can't, you can cross multiply. 10 times 12, does that equal 8 times 15? If it does, then yes, they are parallel. If it doesn't, then no, they are not parallel. If 8 times 15 does not equal 120, then they are not parallel. Okay, this one, 4 says, let's see, it says AC is 36 centimeters, and it says BC, so this whole thing is 27 centimeters. Show that these two things are parallel. Well, they are going to be parallel if this part over this part equals this part over this part. And they give us the whole thing. So what we can do is, if I know that this part's 20 and the whole thing is 36, that means this part has to be 16. Similarly, if this whole thing is 27 and this part's 15, that means this part has to be 12 by the segment addition postulate. Now that you know what the pieces are, go ahead and finish number 4 to show whether or not the lines are parallel by using proportions. Okay, last thing, 2, transversal proportionality. Sweet. This one looks really confusing because we have a bunch of parallel lines. In fact, we have 3 or more parallel lines, and we have 2 transversals. Remember, transversal is just the lines that intersect those parallel lines. So these ones are transversals. So if we have 3 lines and we have 2 different transversals, guess what's going to happen? These are going to be proportional. These pieces are going to be proportional. So A over C is going to equal C over E is going to equal, over CE is going to equal BD over DF. For example, if I was going to give you an example, let's say this part was 1, and this part was 3, and this part was 2. Well, we can set up a proportion to figure out how long DF is. 1 over 3 equals 2 over DF. Cross multiply, and you get DF would equal 6. Again, go ahead and try to put that in your own words after we give you an example. Let's see. Suppose that an artist decided to make a larger sketch of the trees. In the figure, AB is 4.5 inches, BC equals 2.6 inches, CD equals 4.1 inches, KL, this part down here, is 4.9. Find LM and MN. So since they want 2 things, that means we're going to have to use 2 different proportions. So let's say I wanted to figure out LM first. Again, we have parallel trees. These trees are growing straight out of the ground, so we have parallel lines, and we have 2 transversals, this line up top and this line on the bottom. Sweet, so that means all the parts are going to be congruent to each other. So I'm just going to use these numbers to begin with. I have to use 4.5. Again, I like to look at one side at a time. So 4.5 over 2.6 is going to equal, this is the top, it's going to equal the bottom, 4.9. 4.9 goes with 4.5. See how they're coming from the same part? And the part that comes over 2.6, well, that's LM. So to solve this, I would just have to cross multiply and solve. To find MN, I do the same kind of thing. Now I have to use, I don't want to use the 2.6. Since MN is over here, I'm going to use the 4.1 instead. So I'm going to have 4.5 over 4.1. And again, the part that's over 4.5 is that 4.9. And the part that's underneath, that 4.1 is MN. And then I can cross multiply and solve. So that's just how you get your 2 answers for number 5. You can do the same thing for number 6, and you're going to have to use a calculator. And then we're going to go ahead and finish this in class, the triangle angle bisector theorem, because this is the most complex in terms of algebra. All right, so you have the problems that you need to finish, and we've talked about 3 theorems today, and we'll talk about the 4th tomorrow in class.